In this video, I'm going to talk about the curvilinear relationship. So how do we model for curvilinear relationship in data? So essentially, we'll be learning about what is known as the polynomial regressions. You might have heard about the simple linear regression, multiple linear regressions. We'll talk about cases where we model for curvilinear relationship in the data, and we use polynomial regressions, a class of regressions known as polynomial regressions. We also call them as curvilinear regressions to fit the data. So let's get started, and we'll first learn the theory, and we'll take an example to illustrate illustrate the theory that we have learned. So we have understood what is a simple linear regression problem, where we have x and y, and we are modeling for a linear relationship between x and y, right? So typically your linear uh, regression looks like this. We have got y and we have got x. So the regression line is just the linear equations, right? Y equal to beta naught plus beta 1 x. But many a times you won't find linear relationship between y and x. It's not very evident as such. You'll find some sort of a curvilinear relationship. So you cannot fit a straight line through the data points. So that's exactly is the typical case where you cannot fit a linear regression. You rather have to choose something known as curvilinear regressions or polynomial regressions. Okay, so here is an example. So this is an example of rainfall affecting the yield of crops. Okay, and this is the data taken from the US agricultural industry. So here is the data on average corn yield and the rainfall in 6 of the US states between 1890 to 1927. Okay, so this is agricultural data. We have got yield, crop yield in the y-axis, and we have got rainfall in the x-axis. Now we have got these data points. Now looking at this data point, it is very clear that it's very unlikely that a linear regression will fit this data. You cannot have a straight line regression like this which will fit your data. It doesn't seem to be a good fit. Okay, if you just draw otherwise, that's also not a good fit either. So you cannot have a just a straight line which fits your data correctly. If at all you go in for a straight line fit, you're not going to get a very efficient model. Okay, your R square will not be great. You cannot interpret your beta coefficient correctly, and you will have non-normal errors. So your error distribution will not be normal, so that will violate your linear regression assumption, and you wouldn't be able to explain the beta parameters, and you cannot associate t statistics or significance of your coefficients when your error terms are not normally distributed, and so on. So these are the problems that you would be facing if you are going in for a linear regressions. So what is more important, more than of course the validation of assumptions, what is more important is that if it is used for forecasting purpose, it's going to do a very bad job. Okay, for forecasting purpose, you always need a model that actually fits your data correctly. Otherwise, the model will do a very bad job in future. Okay, so for such a data, you cannot use linear regression. That's very evident. So what kind of regression do we use? Here's another example. Okay, so people's income change with respect to the age. Okay, and it's very intuitive that initially the income actually grows with age, but there is a point in time, there is a point in life where your income saturates. It only remains constant for a while, and then it goes down as you grow old. You go beyond, let's say, 50, 60, your income is less likely to grow further. It is only going to you know it is only going to come down, or it is going to grow in a negative rate. Okay, that's because you will be approaching your retirement age, and soon you retire. the only income you will be having is, your income from your savings and investments and income from your pension. Okay, that's not a big money. So that's exactly what, your income initially grows at a very fast rate, and then at one point in time your income saturates, and then it goes down. It of course differs with respect to professions. Some professions, in some professions your income grows with age without declining. For instance, for doctors it's not the case. It's just, normally doctors earn more money when their experience increases and so on. So their income probably will simply be increasing in nature. But for most other professions, you will find the income would be following such a pattern. Now here is this data you can see, and it doesn't fit a linear regression, right? Is it? It will not fit. Some cases where, it is going up. Probably these are medical professionals, but there are cases where, it is going down. Okay, it saturates for most cases, and there are cases where, it is actually going down. Okay, so there is no one straight line which will fit this data. So polynomial regression is a type of regression that you do when you come across such cases. The two examples that we saw last slides, that's typical cases where we go in for what is known as polynomial regressions. So it's a simple variation of linear regressions. There is hardly any difference in terms of specifications. All we need to do is just take the power or different parts of the explanatory variable. So if x is the explanatory variable in this case, we just need to add different parts of x as an additional explanatory variables in the multiple linear regressions model. So normally we use x and we do not use anything else. We need to try x square, x cube, and so on. When we add these terms, these additional terms in the multiple linear regressions, we call this as polynomial regression. And this will do a better justice to the data. Okay, so this will be a better model compared to a linear model. Okay, the question that you might ask me is that what is the order of the polynomial that one should use, because you can have n number of polynomial terms, right? So what is the best number of terms? And we'll see that. Okay, it could be 2, it could be 3, 4. We'll see how to determine what is the best polynomial term. You can have square, cube, to the power 4. So here is a typical example of the yield and rainfall case, and we have used a regression model to fit a linear regression and a polynomial regression with degree 2. That means we have used so y, let's for instance, is yield, and beta naught plus beta 1 x is a rainfall. So this is the linear model. So this is 1, this is the one which is red in color. So the second one is beta naught plus beta 1 x plus beta 2 x square. So this is an additional term. So we have used the degree 2 in the second model. So that's in the that's the green curve. Okay. Now if you look at the two curves, you can easily verify that the model which is having a polynomial term is doing a better job. It is fitting the model, fitting the data better way than the linear model. So look at some statistics. So what statistics do you refer to when we evaluate the model performance of a linear regression? So we look at R square and adjusted R square, right? So for linear fit, it is 0.13. The adjusted R square is 0.13. For a polynomial fit, you can see the adjusted R square has gone up. It is 0.25. So that is, probably I would say the efficiency has increased by twice actually, because it's 0.13 here and it's 0.25. That's like the R square increase by almost 100%, and that's a better result. Okay, the second example that we took, and we also do the same thing. We fit a linear regression and a polynomial regressions. Here also you can see the R square is pretty bad here for linear regressions, and when you took the polynomial terms, it is slightly improving. It's 0.08 instead of 0.4. So the conclusion that we are making here is that when your data is not linearly distributed, you should rather try higher degree polynomials for explanatory variables or independent variables. The question arises: how do we interpret the coefficients in in polynomial regression? Do we interpret in a similar way, or do we make changes to it? Okay. Okay, so that's there is some sort of variation to the interpretations, um, because the term that you are adding here is polynomial in nature. Okay, x square. So when you interpret a coefficient, how do we interpret? We interpret by saying that if x goes by 1 unit, what is the corresponding impact on the y term, or on the dependent variable. Okay, now here if you can say, if x square goes up by 1 unit, how does y differs, right? How does y differs, right? So when x square is equal to 1, right, when x square equal to 1, x could be plus minus 1 instead of just plus 1. So more than interpretation, what is helping us is doing the prediction of the model. So the model can be a better predictor of the dependent variable or the target variable if you are using the polynomial terms. So that's another use of using a polynomial regression in such cases. So here is what we can see here. We have this polynomial regression in place. We have got the weights data, the beta naught, and then we have got the age, and we have taken age minus the mean. Okay, that's just transformation of the variable. Okay, so the way we interpret this is that okay, so here is what we have seen. So change in mean wage associated with 1 year increase in age. So if the age of an individual increases by 1 year, so what is going to be the corresponding change? What is the marginal effect on the corresponding weight? Corresponding wage. I'm sorry. So from 29 to 30, if you just put okay, from 29 to 30, it comes out to be 18. Okay. From 39 to 40, it comes out to be 8.47. Just put the value of age. Okay, so put the value of 39 here and calculate age. Put the value of 30 and calculate age, and you will see not a linear decrease or linear increase. It rather increasing or decreasing. Here it is decreasing, right? From 18 to minus 10, it is decreasing, but at a polynomial rate, not at a linear way. Okay, so linear would be like say 10, 8, 6. So that's linear, right? Where it is decreasing uniformly. Whereas here in this case, you see that it is not decreasing that way. It is following some sort of a polynomial pattern. So how do we choose the order of a polynomial regression? Well, we choose a order of a polynomial regression uh, based on the given data. There's no thumb rule as such that for a particular data the value of the polynomial term should be maximum 2 or maximum 3 or so on. We start with the minimum possible value and then we go on adding it. If at all the higher polynomials are adding values to the model, then it is okay to you. Otherwise, there's no need to go ahead with more polynomial terms when your lower order polynomial terms are doing good. So if you are using x square and that's doing a good job, there's no need to add x cube. But you can try it out. Just add x cube and see if the model is improving. Otherwise, just just use x square term and you need not use x cube. So you try it all possible cases and see which model is the best. So here is we have for the same example number 1, we have fit 3 models: linear model, with x square terms, so that's the green one, and this blue one is x cubed. So we have got three, this polynomial of order 3. So first one is y equal to beta naught plus beta 1 x. Second one is y equal to beta 1 plus, beta naught plus beta 1 x plus beta 2 x square. And third one is beta naught plus beta 1 x plus beta 2 x square plus beta 3 x cube. So we have got third order polynomial in the blue curve. Okay, now how do you measure, how do you see that which one is better? Of course, the linear one is ruled out, that is not a good fit. How do you select from the what is that, quadratic terms, or the order of 2 or order of 3? Okay, so look at the r square values, look at the coefficient, look at the r square value, look at the coefficients, and look at the significance values. By looking at these values, you will get to know what is better. You also look at the distribution of error. So there are assumptions with error, right, in regressions. So just plot the error and see if the error is random in nature, whether there is a pattern or not, whether the error terms seems to be correlated or not. So these are some of the things through which you can actually evaluate the performance of a model, and then select the one that is performing best. If you're doing prediction, it is always good to do with the mean square error or the mean absolute deviation or any of these statistics, and see which one of these model is actually giving the least mean square error, right? Because mean square error should be minimum. Okay, if the square term is giving, or the second order polynomial is giving least mean square error, that's the one to go ahead with. But if third order is giving, then let's go for third order. So one thing that is clear to us is that it helps us improving the performance of the model. The second way of modeling such data, there's nothing known as the transformation. You do some sort of a transformation with your dependent or independent variable, and then you also can model it. Okay, so we'll take an example in this case. So here is the typical case of life expectancy and the per capita GDP. Okay, so this is for different countries, life expectancy and the per capita GDP is for different countries. Now, if you fit such a line, it's not fitting well, because this data is left out, this data is also left out, not a good fit. Okay, but you can actually, instead of going for polynomial terms like x square and x cube, you can try out for transforming either your dependent variable or independent variable and then fit regressions. So here is the typical case. Instead of per capita GDP, you would take the log transformation of it. So instead of per capita GDP, we just took a logarithm of that, and then we fit a linear regressions. Now when we we took a logarithm of per capita GDP and then model with respect to life expectancy, we saw what we are able to, we are seeing that in a linear regression is fitting the line very well. So the transformation is doing the job for us. Okay, and you can see that in the residuals. If you plot the residual for such a model, you see that the residuals are randomly distributed. They're also not they're in both sides of the x-axis, which is what we are expecting, right, in a linear regressions. All right. So how do we use such a transformations? Well, the transformation that we have just performed in the last slide, you will get an estimate for that. Okay, but you can get back to the original variables. Okay, so logarithmic transformations, if log of x is y, x is nothing but e to the power y, in case the base is e. If it is 10, then it should be 10 to the power y. So these are the transformations that you can use to get back to the original variable and then interpret pretty much the similar way that we use for a normal variable. Okay, so we can have various transformation, not just logarithmic transformation. Uh, so not just the polynomial terms like x square and x cube. Just try out log of x. You could also try out log of x square. Okay, so try all possible transformations and see which one of them is actually performing the best. If you're using a prediction, using it as a predictive model, then look at the mean square error and see where exactly the mean square error of the data is minimum, and that's the model to be used finally. So we have performed this 4 type of regressions using a linear fit, a transform log fit with square terms, and then transform fit square. And look at the r square values in this case. Okay, we have also got the root mean square, right? That's exactly what I was talking about, the root mean square error, and that should be the minimum. You will see. Okay. So which one is the least? This is not the least. 7. This is 63, and this is 8 point. So the transform fit square, this model is actually giving us the least root mean square error. So that's the one to be used for prediction purpose. And when you plot the data, you will see which one of these are actually doing the job for you. So plotting actually helps a lot while fitting a polynomial regression or doing certain kind of a transformation to fit data. It's always good to visualize your data first before fitting any of these regressions. So I have already said this. In comparing two transformation, use transformation with lower root mean square error. Okay, so that's one statistics or one matrix used while comparing or evaluating models. The one with the least root mean square error is to be used finally. Okay. In comparing transformations to polynomial regressions model, compare R square. So R square is the best to compare with when you are comparing transformation to polynomial regressions. There are two types of models that we learn, right? One is doing transformation, and the other one is polynomial regressions. But the way you compare them is through their respective R square values. First, just to summarize, we just learned two methods to fit regression models, which has curvilinear relationship between data or variables. Okay, and the first one is fitting polynomial regressions with different order of the polynomial order of the explanatory variables, and the second one is doing transformation. We also learned about how to evaluate the best polynomial regression, what should be the order of the polynomial regression. We also learned how to compare these two models and see which one of them is doing the best job. Thank you so much, and please subscribe.